Continuing with class number 5, I think this is video 3. I'm going to do some examples. Before we go to those examples, there was this was a slide I wanted to point out here, where we have the zone of steam on a TV diagram. This is an area where there's a pretty okay correlation where you could use the ideal gas law for steam. You notice that it's nowhere over in the saturated region over there. It doesn't behave like an ideal gas, but it does over up in here. So it says if T is higher, you can allow smaller V's and still have an ideal gas. To get a sense, look at the TV diagram for water. So for very large V, that's specific volume, the molecules' distances are very large. So you have very small forces between the molecules. Then you can use the ideal gas. So a lot of this has to do, a lot of the ideal gas treatment is that the forces aren't really strong between the molecules. All right, so here is the examples that we're covering in this class. A tank has a volume of 0.5 cubic meters and contains 10 kilograms of an ideal gas, having a molecular mass of 24. The temperature is 25 degrees Celsius. What is the pressure? So in some of this, you will note that we can mix up what we're asking for. So let's see, the given is we have a volume of 0.5 cubic meters. We have a mass of 10 kilograms. Molecular weight, big M, 24, and this should have some units. I believe it should have units of kilogram per kilomole. It's not right that they didn't put that in there, but whatever. And the temperature is 25 degrees Celsius, but like as I mentioned before, it's a good idea to quickly turn that into Kelvin, so you won't forget. So we just added 273 to it. And okay, so the find is the pressure. So one thing we want to do is take the universal gas constant and divide by the molecular mass. So you'll get 8.3145 kilojoules per kilomole degree Kelvin. And if you ask me, I will tell you, yes, I will give you this value. Or you could look it up in the book. I don't know. Maybe I'll tell you to look it up. Well, now I'm trying to change my mind. Anyway, this is kilogram per kilomole. You can see how they cancel each other out. And you get 0.3464. And these are kilojoules per kilogram degree Kelvin. And as I mentioned, I think you should go 346.4, wow, Newton meters, 200 kilojoules into a Newton meter, multiply that by 1,000. All right, so here is the units I think you should think of this as being, right, the equivalent. All right, so some things are worth memorizing. PV equals MRT is a nice one. It just rolls off the tongue. PV equals MRT. Nice. Not N. So you can just rewrite this thing out and go, all right, so that's going to be MRT divided by V. MRT divided by V. So we have the mass, 10. The R is, well, do I want to put the base units in here? We'll continue to use the units for a little while until we're certain. I just wrote M, kilograms. So maybe we won't. Kilograms are 346.9. Newton meters meters per kilogram degree Kelvin times the temperature, 298 degree Kelvin, divided by 0.5 meters cubed. So let's take a look at this thing. We got kilogram, degree Kelvin, We got Newton meter divided by meter cubed, so that turns into Newton per meter squared. So when you get an answer for this, you're going to get 2.065 E6. That's 10 to the 6 newtons per meter squared. So that's going to be the same thing as pascals. So you could either go 2,065 kilopascals by dividing it by 1,000, or you could go 2.0, let's go 65 megapascals. And this is an absolute, by the way. You could subtract out from, if they were kilopascals, you could subtract out 101. Or you could subtract out 0.1013 from this to get gauge pressure. Well, here's the same problem basically, but using, call them English units. We shouldn't really call them English units because it's really, they don't really want anything to do with it. It's really the American. And we can look this up, the information that we need. They did the molecular mass still right there. And I believe that's going to be still like pound mass divided by pound mass moles. I think that's true. So anyway, we'll do the same treatment. Given volume is 15 cubic feet. Mass is 20 pounds mass. Temperature is 80 degrees Fahrenheit. You add 460 to this and you get 540. Yeah, it's 540. Math is hard. 540 degrees Fahrenheit. Yeah, 60 and 80. Yeah, 460 plus 80 is 540. Sure is, all day long. And then we want to get the gas constant. We take the universal gas constant and divide it by molecular. So you get 1545. Here's foot pounds, which is an energy right there, foot pound. Pound mole, which is a new one to me. Degree Rankine, and divide it by this 24 pound mass divided by pound mole. Which doesn't make sense to me that it's the same. 64.38, and these are foot pounds per pound mass, degree Rankine. So I get PV equals mRT. So pressure is equal to mRT divided by V, and the mass is 20 pounds mass. The R is 64.38 foot pounds per pound mass, degree Rankine. The temperature is 540 degrees. Oh, up here above I accidentally wrote an F. I turned it into an R though. See how clever that little boy was that was able to turn that F into an R. And then I don't know what's going on in my brain. There you go. 15. Sorry, volume 15. 15. It's good. I got someone talking loud outside my office. Wish they would stop. R's cancel out. Pounds mass cancels out. That foot gets rid of 2 of those 3 feet, so we have pounds per square feet. Our pressure is therefore 46,354. These are pounds force per feet squared, which we don't need. Let's divide by 144 inches squared, divided by foot squared, 12 by 12, right? So we get a pressure equal to 312.9 psi, and this is absolute, so we call it psi-K. And now we have examples 2.7 and 2.7e in the bag. Coming up on some more examples soon.